Hello everyone and welcome to our calculus notes for section 4.6 on numerical integration. We're going to take a look at two different numerical integration techniques here. The first one, the trapezoidal rule, and the second one, the Simpson's rule. And what numerical integration does, it's finding a way to figure out a definite integral of a function that might be very difficult to integrate, or maybe we don't know how to integrate it yet, or of some type of function that we don't actually know what the function even is, but we can determine some of the function values. This can be extremely useful in real-world situations where things fluctuate pretty rapidly, and there might not always be a perfect formula to give us the values, but we do know the values, and so therefore we can calculate these definite integrals using numerical integration. So let's take a look at the trapezoidal rule first, and you can see the rule down here, and that's what you're going to eventually want to use and memorize. But let's talk about how this works here. So the idea is we're still looking for a definite integral from a to b of our curve f at x with respect to x. And so you can see our curve f at x right here. And let's just say a happens to be right here and b happens to be here. And so we've equated this in the past to the area under the curve, and that's an easy way to think about it. Now what we can do is split this into a couple different intervals. Do that here. And before, what we did is we actually looked at some rectangles that would approximate this area. So these would be left-hand rectangles, and we just found the length times the width and then added them all up. Now in this case, what we want to do instead of that is actually look at trapezoids. And so what we're going to do is we're just going to join the two y values here with a straight line to create trapezoids. And so now we have three trapezoids here that can approximate the area. And notice that that's going to be a lot better approximation than using just rectangles. So let's think about the area of a trapezoid and figure this area out. So here is our trapezoid, and the area is going to be 1/2 b sub 1 plus b sub 2 times h. So let's try to figure out where all these things are. So first off, b sub 1 would be one of the parallel sides, and b sub 2 would be the other parallel sides. And then the height is actually going to be the perpendicular distance between the two right there. Now what we want to do is be able to use the function to get these values. And so we're going to call, right here at a, we're going to call that x sub 0, and then this next one will be x sub 1. And what that's going to allow us to do is figure out b1 is going to be f at x sub 0, and then b2 is going to be f at x sub 1. Now we're also going to have to figure out what length the height is. Now the height right there is what we've been calling delta x. And so that's going to be the b minus a over n, and that's going to be our height. Okay, so if we were to just take the area of this very first trapezoid here, we would get 1/2 times f at x sub 0 plus f at x sub 1 times the height, which is b minus a over n. And that's the first trapezoid there. Now we're going to move on and add up the other ones here. And so if we move on to the second trapezoid, we're going to call this x sub 2 right here. And so notice our b1 and our b2 actually will switch now. And so this one is now becoming our b1 and this is becoming our b2. But notice here the delta x doesn't change. So that's going to stay the same. So let's go ahead and get the area of the second trapezoid, and we're going to add it there. And so that one's going to be 1/2. Now we're going to be at f at x sub 1 plus f at x sub 2, and times the height, which is still b minus a over n. So hopefully we can see there that that b sub 2 was f at x sub 2. And if we go on to our third one now, we change once again. And so this becomes our b1 and this becomes our b2. And so now we have f at x sub 2 here, and this one's going to be f at, well, x sub 3. We'll just call that x sub 3 down here. And so if we add in the area of that third trapezoid, notice your delta x will also be the same, doesn't change. And so the third trapezoid here would be 1/2 times f at x sub 2 plus f at x sub 3 times the height, which is b minus a over n. Okay, so this would be an approximation of the area under the curve, which is also the definite integral for this function from a to b. And what you're going to notice is all of them have a common 1/2 there. So we're definitely going to have that 1/2. And then all of them also have a b minus a over n, which is that delta x, or the height of that trapezoid. So we're going to have times b minus a over n. And now we're going to add everything up on the interior. So we have in the first trapezoid f at x sub 0 plus f at x sub 1. In the second trapezoid, we're going to have f at x sub 1 plus f at x sub 2. And in the third trapezoid, we're going to have f at x sub 2 plus f at x sub 3. So if we look closely here, what we're going to find is that we're going to have two f at x sub 1s in here. The reason being is one of them is working in this trapezoid, and then the other one is working in the second trapezoid. And the same thing's going to happen for f at x sub 2. It's going to be in the previous trapezoid and then in the next trapezoid. But you'll notice on the outsides here, the f at x sub 0 and the f at x sub 3, that length is only going to be used in one trapezoid. And so when we add all this together, we're going to get b minus a over 2n times 1 f at x sub 0 plus 2 f at x sub 1 plus 2 f at x sub 2, and then plus only 1 f at x sub 3. What we've discovered here is this coefficient pattern of 1, 2, 2, 1. And you're going to see that right down here. Okay? And the reason is each of those bases on the interior is going to get used twice, and the bases on the exterior of your interval are only going to get used once. So the trapezoidal rule that we've kind of just looked at, we can add in as many subintervals as we want in here, and that's going to be n, is going to be b minus a over 2n. And hopefully that part makes sense to you. You can see the b minus a over n is just going to be the delta x part, okay, the delta x part right there. Now the 2 is going to come from the 1/2 that came from the area of the trapezoid. And we're going to see 1 f at x sub 0, and that's the first height right there. 2 f at x sub 1s, we're going to see it's the height from the left and the right trapezoid, and 2 of the next one. And this is just going to go on and on and on until you get to the very end, and then you only have 1 of the very last one. So this right here will give us an approximation for the area under that curve, which is the same as the definite integral from a to b. All right, so let's go ahead and use the trapezoidal rule to approximate the integral for n equals 4. All right, so we want to find the definite integral from 0 to pi of the sine of x with respect to x. Now, we haven't really talked about the integral for sine yet, and so we're going to use trapezoidal rule to kind of approximate this. We're trying to find the area under this curve from 0 to pi. And so we are going to set this up with n equals 4, meaning 4 subintervals. So we can draw those in here. And then we are going to be using trapezoids here. So we can just draw that on there. All right. Now, when n equals 4, we want to go ahead and find delta x. And that's always going to be b minus a over n. And so that's going to be pi minus 0 over 4. And so we're going to get the pi from the upper limit of integration. We're going to get the 0 from the lower limit of integration right here. Okay? Now we're going to divide by 4 because n is equal to 4. And so what we're going to find is the width, or the delta x, is going to be pi over 4. And what that allows us to do is to figure out all the x values that we need for the trapezoidal rule. So we are going to start at 0, and then we're going to go pi over 4 away. We're going to go 2 pi over 4 away. and then 3 pi over 4 away, and finally 4 pi over 4 away. Now some of these do simplify, and so if you want to simplify it, you can. This would just become pi over 2, and then the last one, of course, is just pi. Okay, so that's going to tell us where all of those x values are. So we're going to go ahead and find the area, which is the same as the definite integral from 0 to pi of sine x with respect to x. And this is going to be an approximation here, so this won't be exact. And we're just going to use this rule here. So we have b minus a over 2n. So b is going to be the pi, and then minus 0, a is 0. And it's going to be over 2 times n, and n is 4. And it's going to be now f at x sub 0. So it's going to be sine at 0, so right here at the starting point. And now plus 2 sine of pi over 4. So remember, we need 2 of the pi over 4s because it's in both trapezoids. And then plus 2 sine of pi over 2. And again, it's because that pi over 2 is working in both trapezoids there. And then plus 2 sine of 3 pi over 4. And that's because it's here and here. And then finally, 1 sine of pi. Now at this point, you can simplify this down. If you do know what some of these trig values are, you can plug those in, or you can get good at plugging this into your calculator. So I'm going to show you just plug it into your calculator. All right, so I'm going to plug this into my calculator, and this is sometimes the most difficult part of the whole process, is getting this plugged in, because these can be a little bit lengthy, and so you just really need to practice with your calculator that you're going to be using. And so we're just going to start off. We get pi minus 0, and then divided by 2 times 4. And again, if that's easy, you can write in 8. That's totally acceptable. And then we're just going to have sine of 0. So one note here, make sure you are in radian mode whenever you're doing trig. So sine of 0 will close off the angle. And then plus 2 sine of pi over 4. And again, we'll move out and close off the angle. Plus 2 sine of pi over 2. We'll move out, close off the angle. Plus 2 sine of 3 pi over 4. Move out, close off the angle. And then the last one is just going to be plus the sine of pi. And then we're going to close that off. And we can see we have an approximation of about 1.896. All right, again, so very important to practice using your calculator when you get this. Now, how close were we? Well, if we think about how we're going to find this, if we wanted to find the actual definite integral, we would have to think, well, what function gives us the derivative of sine? And that's going to be negative cosine, right? Because the derivative of cosine is negative sine, so to get positive sine, you'd have to have the negative cosine. And then if we use fundamental theorem of calculus, we'll put 0 and pi right here. And we're going to plug in pi first, and then minus, plugging in 0 next. And if you think about cosine of pi, that is negative 1. And then cosine of 0 is 1. And so the actual answer is 2. So our approximation is just a little bit of an underestimate. And you can see that when you draw those trapezoids. But it's a pretty good approximation, and it's a lot better than you'd get with rectangles. All right, so let's give this a try with letter B. So I said we're going to use numerical integration when it would be difficult or almost impossible to figure out these antiderivatives. And if you look at this one right here, and you try to use u substitution with the composite function, what you're going to find is when you get du, you have negative 3x squared dx. And when you solve here, you're going to see that you don't have the variable portion inside the integral here, and so that makes it very difficult to solve. So these numerical integrations are going to really help us when we go to figure these definite integrals out here. All right, so let's just take a look and analyze here what we're doing. we're going to go from 0 to 1. So here we are at 0. Here we are at 1. It looks like that's 0. And n is going to equal 4 in this case. Okay, so we're going to split this into 4 equal subdivisions. And so we do need to find delta x so that we can find our x values. And so that's going to be from 0 to 1, so b minus a over n, and that's going to be 1/4. And so if we start here at 0 and we go 1/4 away, we'll be at 1/4. If we go another 1/4, we'll be at 2/4 or 1/2. If we go another 1/4, we'll be 3/4. And if we go another 1/4, we'll be at 4/4 or just 1. Okay, and then we can draw our trapezoids in. You can see this gives us a pretty good approximation, maybe until here at the end. So again, we'll have another underestimate, but it'll work. So we'll just say approximately, and we're going to use trapezoidal rule. So remember, it's going to be 1/2 because of the formula, and then it's b minus a over n for the height of each of these trapezoids. So we have 1 minus 0 over 2 times 4. Okay. Now, we only want one of the first y value, and so that's going to be the square root of 1 minus 0 cubed. Now we want 2 of all the ones on the interior. So we want 2 times the square root of 1 minus 1/4 cubed. So we just have to plug that into the function. And then we want plus 2 times the square root of 1 minus, now we're at 1/2, so 1/2 cubed. And then plus 2 times the square root of 1 minus 3/4 to the third power. And now we're at the very end of our interval, and so this one is going to be just 1 times the square root of 1 minus 1 cubed. Okay, so you can go ahead and type this whole thing into your calculator at this point, or you can try to simplify this down to make typing it into your calculator a little bit easier. I think I'm just going to show you using the calculator. So we'll have 1 minus 0 over 2 times 4, or you could just put 1 over 8. And then we'll have the square root of 1 minus 0 to the third power plus 2 times the square root. So we would get 1 minus, this one's going to be 1/4 to the third power. So we do want to use parentheses here. And this is where you can get in trouble a little bit. So you really want to be careful how you're using your calculator. So that's it for that one. We'll move outside the radical, and then we have another 2 radical. It'll be 1 minus. And now we're going to plug in 1/2. So that's going to be 1/2 to the third power. We'll move outside the radical, and plus another 2 radical. This one's going to be 1 minus 3/4. All right, 3/4 to the third power. We'll move outside the radical, and now we want square root of 0, which we know is 0, so we don't actually have to put it in there, but you can if you would like. And so we can see that we get about 0.797. All right, so again, once you set up trapezoidal rule, you just need to type it into your calculator, or you can simplify things down first and then enter it into your calculator, but just be really careful when doing that. All right, so there is an approximation for that definite integral of something we really don't know how to find the antiderivative of quite yet, or it's just really difficult to do. So how would you make this a better approximation? Well, you could just add more trapezoids. So you could increase that n number until you get as good of an approximation as you'd like. All right, so next we're going to use something called Simpson's rule. And Simpson's rule is kind of like trapezoidal rule, where we figure out the area under a curve of something else that we know. And so what we do in this case is we actually use tiny little parabolas to wrap even closer around the function we're approximating. Now, you might say, well, we don't know the area formula for a parabola, right? Because trapezoid you know, rectangles you know. What's the area under a parabola? Well, we do know the area under a parabola, and I'm not going to do the whole proof here, but the area under a parabola is going to be the definite integral of ax squared plus bx plus c. And so because of this, you can actually find the area under that parabola using the definite integral of this form. And so when all is said and done, and you do the same type of process as you did with the trapezoids, you get this formula right here. You have b minus a over 3n. And so hopefully you can see that b minus a over n, that's the width. And then in this case, you actually divide by 3. Now, when you move to the interior, we actually have this alternating pattern. And the coefficient pattern in this case is going to be 1, 4, 2, 4, 2, 4, 2, 4, 1. Okay? So hopefully you can see that there. 1, 4, 2, 4, 2, 4, 2, 4, 1, all the way to the end. So we're going to do this kind of the same way, and we're going to actually evaluate the same definite integral, but now we're going to use Simpson's rule to evaluate this integral. Okay? So again, we have our same function, sine of x, from 0 to pi, and we want 4 subintervals. So here is 0, here is pi, and we want 4 intervals. We're going to split those up here. And this process is the same whether you're doing Simpson's or trapezoidal. Okay? Now, the way this parabola works, it actually uses 3 points. Basically, we're going to have a parabola that goes through all 3 of those points. And you can see the approximation is now going to be really close. So there is one parabola. It takes 3 points. And then we actually have another parabola, and it's going to go starting at that 3rd point there, and then going through the next 3 points. We get this parabola right there. Okay, well, we still have to do the same where we have n equals 4, and we still have to find our delta x. And so that'll be b minus a over n, which in this case is pi over 4. And so we're going to start at 0, go 1 pi over 4 away, 2 pi over 4, which is pi over 2, 3 pi over 4, and then finally 4 pi over 4, which is just pi. Okay, so now we're going to use this formula right here to calculate an approximation for the definite integral. Okay, so now we're going to have b minus a over 3n, so 3 times 4. And we're only going to have one of the very first ones, so that's just going to be the sine of 0. And then we're actually going to have 4 of the next one. So we're going to have 4 times sine of pi over 4. And now we're going to go back down to 2. So we're going to have 2 sine of pi over 2. And then we're going to go back up to 4. It's going to be sine of 3 pi over 4. And then finally, we're at the end of our interval, so we just want one of those, and we want 1 sine of pi. Okay, so you notice we had to have an even n value, so that when you split this up, you can put this into a certain number of parabolas, each having 3 points. Okay, now from here, we can either simplify, or again, just type this into our calculator. If we did simplify, notice we would have pi over 12 times the sine of 0, which is 0, plus 4. Sine of pi over 4, if you remember those from the unit circle or you've memorized them, is the square root of 2 over 2. And then 2 sine of pi over 2. Sine of pi over 2 is 1, so this will just be 2 times 1. And then plus 4 sine of 3 pi over 4. And 3 pi over 4 is also rad 2 over 2. And then plus sine of pi. and sine of pi is 0. And so if you do this, you can cancel a little bit here. So that would just be 2 and 2. So you would get pi over 12 times 2 rad 2 plus 2 plus 2 rad 2. So we could add this again. You get pi over 12 times 4 rad 2 plus 2. And this might be a little bit easier to type into your calculator there. So we'd have, again, make sure you're in radian mode, pi over 12 times 4 rad 2, get out of the radical, and plus 2. And you can see our approximation is now going to be 2.005. So the way these parabolas shape up, it's a little bit of an overestimate in this case. And if you remember what our actual was before, the actual was 2. And so we're within 5 thousandths just by splitting this into 4 intervals. And so Simpson's rule is a really, really good approximation of this definite integral. All right, let's move on and try our next one here. Okay, so again, n is going to equal 4. And so delta x is going to be 1 minus 0 over 4, or 1/4. And we're going from 0 up to 1, and we're splitting it into 4 intervals. And so that means we're actually going to use 2 parabolas here. It's interesting. And we do need our x values here. And so we're going to start at 0. We're going to go 1/4 above that, 1/4 above that, which will be 1/2, 1/4 above that, which will be 3/4, and 1/4 above that, which is 1. Okay, and so now when we do our approximation, we'll have b minus a over 3, now 3 times n. And this is going to be the square root of 1 plus x squared. So 1 plus x squared. The very first one will be 0 squared. And then we want 4. So it goes 1, 4, 2, 4, 1. So 4 square root 1 plus 1/4 squared. And plus 2 square root 1 plus 1/2 squared. And I do use parentheses when I plug this in. Keep it straight there. And then we want plus 4 square root 1 plus, and now 3/4 squared. And then my last one will just be 1 square root 1 plus 1 squared. Okay, now again, you can type this entire thing into your calculator, or you could, simplify this down a little bit before you plug it into your calculator. And so I'm going to do that here. You're going to get 1 over 12. The very first one is going to end up being the square root of 1, so that's just 1. The next one will be 4 times the square root of 1 plus 1/4 squared, so that's plus 1 over 16. The second one will be 2 times the square root of 1 plus 1/2 squared, which is 1/4. The next one will be 4 times the square root of 1 plus 3/4 squared, so that's 9 over 16. And then plus the square root of 1 plus 1 squared, square root of 2. And we could simplify this down even more. We'll have the 1 and then 4. So 1 plus 1 over 16, so that's 16 plus 1, 17 over 16. And then plus 2, 1 plus 1/4. So that's 4/4 plus 1/4, or 5/4. So square root of 5/4. And then 4, 1 plus 9/16. So 16 plus 9 will give us 25. And then square root of 2, can't do anything with that. And we could simplify this even a little bit more. Why not? So this would be 4 rad 17 over 4, because the square root of 16 is 4. This one would be 2 rad 5 over 2, because the square root of 4 is 2. Next one would be 4 times, let's see, square root of 25 is 5, and then over 4, and then plus rad 2. And a couple of these are easy to simplify. So the 4s would cancel here. You'll be left with the square root of 17. The 2s would cancel here. So you got the square root of 5. The 4s would cancel here. So you have 5. And then you have the square root of 2. And from here, we could type this into the calculator. And so we would have 1/12 times 1 plus the square root of 17 plus, oops, let's get out of that radical. So plus the square root of 5 plus 5 plus the square root of 2. And we get about 1.148. And usually we like to go to 3 decimal places there. And so that would be an approximation of the area under this curve or this definite integral, which would be pretty tough to find because, again, when you look at the inner function, you don't have the x part of the derivative, the 2x. And so this would be pretty tough to find. But all in all, this is how Simpson's rule would work to find that definite integral. And so yeah, again, you could type this whole thing in your calculator, but you'd have to be very careful when you did it. Maybe you trust your skills of simplifying a little bit better and a little bit less on your calculator skills, then you could do it that way as well. Now, where this numerical integration really shines is in these real-world examples. And so here we have a car. It starts driving at noon, and then it takes its velocity every hour for the next 10 hours. And so, yeah, this velocity can go up and down, and we don't know exactly what's going on in all the points, but we do have some of these points here. And if we want to find out how far it travels, basically, if we integrate this rate or we find the area under this curve, we're going to figure out how far it traveled. So let's just think about this with the trapezoidal rule first. So we can just join all these points with trapezoids. Straight lines here. So the car starts running into some traffic. Pretty long journey. And so we're going to break this into 10 intervals for the 10 hours. Okay. And so our distance traveled, the distance traveled will be that definite integral from 0 to 10 of whatever that function is. And maybe this is a rate over time function or velocity over time with respect to t. Now we don't know what that function is, and so we are going to use the trapezoidal rule here to estimate it based on all these values that we have, the exact values right over here. Okay, so our distance traveled will be b minus a. So we're going to get 10 minus 0 over 2 times n, and we had 10 there. So you can see the delta x equals 1. And then we're going to want one of the very first y values. So the first y value here is just at 0. So we want one of those. So notice we don't have a function. We can't actually plug anything in. But when you're looking at f at 1, f at 2, f at 3, they're really given by the function values right over here. So that's kind of nice. So we want 2 of the 59. We want 2 of the 71. We want 2 of the 68. We want 2 of the 54. We want 2 of the 42. All right, we're just going down. We want 2 actually of all of these. We want 2 of the 30. We want 2 of the 22. We want 2 of the 15. We want 2 of the 10. And we only want 1 of the 7. We just fit it in there. All right, so now this just becomes a big calculator problem again. And what it ends up being is 374.5. And since this was miles per hour, when you integrate the miles per hour, you actually get miles. So we're going to approximate that this car drove 374.5 miles on this trip. Now, if you want to do the same thing with Simpson's rule, which we know is going to be a little bit better, the first thing you got to do is make sure that we have an even number. We have an even number here. And so is n an even number? Yeah, n is going to equal 10. So when you go to figure out those parabolas, okay, you're going to see that it will go from one endpoint through a point into another one. So some of them might be underestimates, some of them might be overestimates, but you can see that we do get an exact number of parabolas. Okay. Now if you notice, if you use trapezoidal versus Simpson's rule, that all you have to do is change a couple things. So you can actually just copy this, and we'll change out the things that we need to change out. So one of those things is this needs to become a 3 instead of a 2. And then the coefficient pattern is going to go 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. And so this is a 4, and then the 2, and then the 4, 2, 4, 2, 4, 2, 4, and 1. And so that's how we have to alter it so that this is going to be looking like Simpson's rule. And now when you calculate this, just typing it all in, you get about 383.667 miles. So a much better approximation. And that is how you use trapezoidal and Simpson's rule to estimate the area under the curves, especially when you don't have functions and all you have is a couple data values. All right, so that has been 4.6 numerical integration.